Continuing with section 1.9. A mapping T from Rn to Rm, I'm over here, is said to be onto Rm if each B in Rm is the image of at least one X in Rn. Or, in other words, we can say T is onto Rm if for every B in Rm the equation Ax is equal to B has at least one solution. So at least, remember, means at least one means one or more. At least 5 means 5 or more. So when we say at least one, it means it should have one, or it may have more than one solutions. But having no solution will mean that the set is not onto. The other property that we are looking at is one-to-one property. So when is a function one-to-one, or when is a mapping one-to-one? So we say a mapping T from Rn to Rn is said to be one-to-one. We often write it like this, 1-1. If each B in Rm is the image of at most one X in Rn. Or T is one-to-one if for every B in Rm the equation Ax is equal to B has a unique solution or no solution. So for being onto, remember, unique solution is okay, but no solution will make it not one-to-one, not onto, sorry. But if there is no solution or there is a unique solution, the mapping is one-to-one. Next, we have theorem 11, and remember we started section 1.9 with theorem 10, which was about the, if you go back and see, remember, okay, so we said that T be a mapping or linear transformation, then there will be a unique matrix A. So the theorem 10 was telling us about the existence of this matrix, which we can easily find by knowing where the special vectors E1, E2, E3, so on, where they are mapped. So now theorem 11 is saying let T from Rn to Rm be a linear transformation. Then T is one-to-one if and only if T of x is equal to 0 has only the trivial solution. So we already explained when will a function be transformation be, linear transformation be one-to-one. We already defined. We said it will be one-to-one if the equation Ax is equal to B has a unique solution or no solution. But now in the theorem, we are saying that T is one-to-one if and only if the equation Tx is equal to 0 has only the trivial solution. So if and only if means that if one thing happens, the other happens. Okay. So if we know that T of x is equal to 0 has only the trivial solution, then we say the mapping is one-to-one. And if we know that mapping is one-to-one, it means T of x is equal to 0 will have only the trivial solution. So these theorems, you don't need to know the proofs of these theorems, but you should know how and where to apply and when to apply these equations and answering the questions asked. So theorem 12 says let T from Rn to Rm be a linear transformation and A be the standard matrix for T, then what it means is that A and B are both correct or both false. So if one happens, then we can say the second happens. If one doesn't happen, then this other cannot happen. So we say we have a linear transformation from Rn to Rm, and we know that A is the matrix, standard matrix. We say T maps Rn onto. So in other words, we can say that the transformation is an onto transformation if and only if the columns of A span Rm. And now, when can this happen? If you recall from previous sections, there are a bunch of things which go over here. So T will be onto if A spans the Rm. Okay, columns of A span Rm. In order for them to span Rm, what else we knew? That columns of A are linearly independent. Or we say that the equation Ax is equal to B will always have a solution for B. Or we said we can say Ax is equal to 0 has only the trivial solution. So these are different things that come along with this. Now T is 1 to 1 if and only if the columns of A are linearly independent. So if they are linearly independent, then we can, so first thing we can say, you see the definition which we started with, that T is 1 to 1 if each B in Rm is the image of at most one X in Rn. Now this is really very hard to prove. So the exact definition we cannot, because sets have infinitely many elements. We cannot check each and every element. So we have to use some other statement which should be equivalent to what we have here. So here is one statement is already given in the definition, that T is 1 to 1 if for every B in Rm the equation Ax is equal to B has a unique solution or no solution. But now this theorem 12 gives us another way to look at this one. It says T is 1 to 1 if and only if the columns of A are linearly independent. And so it gives us both for conditions for both the onto and 1 to 1. So let's look at this example 2. So it says find the standard matrix for the transformation from R2 to R2 that rotates points through negative pi over 4 radians. So what will the matrix be? We already know, because this is in R2. So we are in space R2. We already saw up there, I think it was the second matrix here, cosine theta, negative sine theta, and sine theta, cosine theta. So this number 2, this is for rotation. So theta is given, we plug in and we just know, if you know what it is, then that is good. So you plug in, so it was cosine theta, so cosine of negative pi over 4. In the second entry we had negative sine theta, so I have negative sine of negative pi over 4. And then in the second row, in the first column, we have sine theta, so I have sine of negative pi over 4. And then the second row, second entry was cosine theta, I have cosine of negative pi over 4. Now remember, sine of negative x is equal to negative sine x. But cosine of negative x is just cosine x. So this is again some properties of the sine and cosine function. So this is the showing that this is an even function and the sine is an odd function. So this is, if you recall the definition of even and odd function. So when I have cosine of negative pi over 4, it will be the same thing as cosine of pi over 4, which is square root 2 over 2, but if you see, we can simplify and write it like 1 over square root of 2. So if you have a cosine of negative pi over 4, it is just going to be cosine, the same thing as cosine of pi over 4. But if you have a sine of negative pi over 4, you will get negative sine of pi over 4. Now, cosine of pi over 4 and sine of pi over 4 have same value, so it's 1 over square root 2. So we get, from here we will get negative of 1 over square root of 2, because the one negative sign is already present in the matrix, and then one negative sign comes out because of the sign function being odd. So negative makes it positive here. And then in the second row, sine of negative pi over 4 is negative 1 over square root of 2, and then cosine of negative pi over 4 is 1/2. So this is our final answer. Looking at the next example, let me first erase this. Okay, so next thing we are going to look at is part B. So what is the part B asking? It's saying, okay, so we have to give the matrix of transformation. What is the transformation? It is again going to be from R2 to R2, and it is a horizontal shear that leaves E1 unchanged and maps E2 into E2 plus 3E1. Okay. So how can we do that? Well, I have the matrix written here. Not this one. This is the matrix that will reflect about the what the question there. Okay, so I was looking at C part. Okay, B is 1031. Why is it that? Because what it is telling me is that in part B, what it is telling us is that the shear leaves E1 as it is, which means in this case T of E1 is just E1, which is 1, 0. And T of E2 is equal to E2 plus 3E1. Now what is E2? E2 is 0, 1 and plus 3, 1, 0, which is going to give you 3, 1. So remember from before, the matrix is going to look like A will be equal to T of E1 and then second column T of E2, and there are only two these vectors in on the x. There are two axes, so there are two vectors on the axes, so we have only two columns for A. So first vector is 1, 0 and the second is 3, 1, so that the matrix for this transformation B is here. Okay, now looking at number C, part C, this is saying, so we have to find the standard matrix for the transformation from R2 to R2, which first reflects points through the vertical axis x2 and then rotates points by pi over 2 radians. Okay, so how do we do this one? So we have two matrices now. So first, we want to reflect over the vertical axis. So if I have a point over here, it will go here. So what matrix I need to multiply the vector with? So we think of this as a vector, and then we multiply it by the matrix. So the matrix was 1 0 0 negative 1. Okay? This is the matrix for the reflection about the vertical axis. Okay, and then second thing we do is change the rotation. So rotation by pi over 2. So we use our same matrix as before, cosine theta minus sine theta, and second row is sine theta cosine theta. But theta in this case is pi over 2. So I plug everything in here. This is the second matrix A2. So this was A1, if you can see that. This is A1. Let me make it clear. And the next is A2. So this is A2. And this is, plug in the theta, which is pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. So I get the matrix 0, negative 1, 1, 0. Now when we are going to combine, how do we combine them and get one matrix? So our A will be, so remember we are multiplying the vector on the right of the matrix. So you cannot just put these A1, A2 in any order. You have to be careful. When we have AX, so we want to find A, and what we did was we first applied A1 to X. So this is how we went. We did A1X. So what did it do? It reflected the vector about the vertical axis. And then once we had that, then we multiplied by A2, which rotated the vector by pi over 2. So it means you have to have the A vector will be in this order. So A will be equal to A2 times A1, not A1 times A2. Okay, you cannot, you have to be careful when finding the products of matrices here. So I just now take the two matrices and I multiply, and this is what I get. So I got this matrix. Okay. So this is the matrix. Okay. The last part D in there. So we have this transformation which is given now like this. Now we are not given the we are not given the matrix A, but and we are not given the images of E1, E2, E3. So what we do is we find the images using this transformation. So the transformation is given like this, and you note here, because we have it doesn't say in the, it says in the problem actually in the beginning that it is T is going from R3 from R2 to R2, right? In the D part, notice here we are getting a 3 component vector. So we are going in R3. So T starts with from R2. So T is a mapping from R2 to R3, unlike the previous one. Okay. So here, because here we have a 2 component vector, and here we have 1, 2, 3, actually 4, R4 is going to R4. So there are 4 components. So we want to find out what is the matrix of the transformation. So what we do, we find the we will find the images of the E1 and E2, E3, because we are in R2, so we will have only 2 components, right? X1 and X2. So E1 and E2, that's what we want. What is T of E1? What is T of E2? So that's what I did here. T of E1 means T of 1, 0, and this is, I rewrote the the transformation here so that we don't have to go back and forth. So we have, so the transformation says the first component is 2x2 minus 3x1. Now in E1, the first component is 1, second component is 0. So when I plug it in here, so I get 2 times 0 minus 3 times 1. So I get a negative 3 for the first component, comma, second component is x1 minus 4x2. So what happens, x1 is 1 minus 4x2, x2 is 0, so we just get 1. And then the third component is just 0, so we just put 0. And the second last component is x2, and x2 is 0, so we have 0, 0. So we get negative 3, 1, 0, 0. This is the image of T1, E1 under T. In the same way, now we will find the T of E2, which means T of 0, 1. So working in the same way as before. So this will mean first component will be 2 into x2. 2 into x2, but now x2 is 1, so I get 2, and then it says minus 3x1. x1 is 0 here, so we get 2 minus 0, which is 2. So we get the image of E2. And now we just put it in our matrix. So A will be equal to the matrix with 2 columns, where the columns are the images under T of E1 and E2. And so here is my, so what I did, took this one, put it in the first column here, and took the second vector and put it as a second column of the matrix. So that's the matrix A. Okay, I'll stop here, and then we will look at the rest of the examples in the next video.